an appropriate way to get started. So we are going deep. That's this one here. The first part is, this is the introduction lecture I'm going to start with shortly, and that's what I mentioned. And then we're going to explore basically, as soon as we are leaving our Milky Way galaxy, as we're going to do, looking around us, what we meet, and then we go travel a very, very long distance till the edge of the observable universe. That's that exploration lecture. I need to explain why or how we know all these structures. This has been because of great efforts by lots of astronomers and billions of dollars in investments over many decades of deep sky surveys with specific telescopes. I'll talk about those projects briefly here, and then we'll talk about galaxies in general, the classification, what kind of galaxies there are, etc. So this is more or less an astrophysical part of this course. And then when we start to talk about the expanding universe, we essentially are going into what is called cosmology. Cosmology is the study of the universe as a whole. You're not worried about individual galaxies or clusters of galaxies anymore. You just look at the whole thing and you treat it as one volume. And then it's amazing how much you can figure out based on modern physics and on especially the general theory of relativity. I'll come back to that when we get to that point, that I advise you to, in your free time, to go back to those lectures in the previous course about theories of relativity as a foundation for cosmology. When the universe is expanding, you need to figure out what you mean when you talk about distance. And then we go into the real, what is called Big Bang cosmology. That's the theory based on the theory of general relativity about studying the universe as a whole, and obviously its history. The cosmic microwave background radiation, you may have heard of that, is an extremely important component of that. Only about 50 years ago, whatever it was, that it was discovered. It made cosmology to an observable science rather than just a philosophy that you think about the universe, but which we have been doing most of the human history. But now we really can start make observations that give us a lot of information. It's absolutely mind-blowing how much we now understand of this, of the evolution of the universe. But also, it's astounding how many seemingly very basic questions we can't answer. And that's the topic of the last lecture. Kind of making a list of the real big issues that are still remaining. And that kind of closes the cycle of this course, because in the first lecture, which let me start at now, we will ponder a little bit, and I'll try to challenge you to think about this for yourself. Is who are we in the universe as human beings on our planet, and what can we understand, and what we how big is this whole thing, not in only physical size, but in complexity. What can we imagine that we as mortal human beings can ever understand of the grandeur of the entire universe? So that's kind of a philosophical start, and at the end we will reach the major questions that are still remaining, which gives food for thought of who we are when we explore the universe. Okay, already starting kind of philosophically. You know me by now. Occasionally I make those excursions. I feel very strongly about this. Not just about technical stuff. It's it's a very large component is a philosophical approach to who we are as humans and how what we can ponder about when we observe and study the universe. So that's kind of a teaser for this new course, this last course. I'll enter full screen here. As always, we have a handout here. I think I'll open it just in case we need it. So the title Going Deep has a double meaning, and I'll come back to that. And that's kind of the scene, the theme of this whole course. As always, I'll look at a little bit of history, how we started, and it is amazing that it was just over 100 years ago that there was a debate, a very famous debate, where we didn't even know if there was a universe outside the Milky Way or if the Milky Way was the whole thing. Just 100 years ago, and look at where we are now. So we need to have that historical perspective a little bit. We are always looking back in history. So our telescopes are time machines. This is extremely important to realize, especially now that we are going to travel such unbelievable distances. And then I'll come back to the philosophical start, which I just kicked off. What can we know? Who are we, and what can we think that we could ever understand of the whole thing? Okay, it's a very relatively short lecture, this first one, but it is really setting the scene for this story that is going to evolve in this course. Usually I start all my courses, as you know, with a lecture called Sense of Scale. A couple of years ago, I changed the title, because the title of this lecture is Exploring the Universe. Because in a way, it's I could call it a nonsense of scale. There's no way that you can imagine the sheer size of the distances and the volume of space that we're going to discuss in this course. Just remember what I suggested for you to think about when you want to imagine what the speed of light is like. You travel 7.5 times around the Earth in 1 second. That is the speed of light. So a light year, and we had this discussion already in the second course, I believe. The start of leaving the solar system. If you then think about traveling with that speed of light, you start on your birthday and you travel day in, day out, night and day, week in, months after months, until your next birthday. With that crazy speed, you cover 1 light year. In that second course, Leaving the Solar System, we essentially looked at a bubble up to a radius of some 5,000 light years. It increased a little bit during the discussion to something like 7,000 light years. Anyway, it doesn't matter. Something like that in order of magnitude 5,000 light years. If you want to have an imagination when you needed to start until to have reached 5,000 light years at the present day, you would have to start at the Middle Kingdom in the Egyptian culture, which is about 2000 before the Common Era. And then, 3,000 before the Common Era, plus 2,000 in the Common Era that we are, and you have traveled 5,000 light years. So you have to travel with that crazy speed for all of human history, basically, to cover only 5,000 light years. And then we went into the discussion about the Milky Way, which is, and I explained that there's a visible part of the Milky Way, which typically people call something like 100,000 light years across. But I explained in the course, going through that course, that actually, if you want to include the dwarf galaxies around our Milky Way, and also the halo the various definitions of halo, including the so-called dark matter halo, that you would have to extend this to about a radius of 500,000 light years. So that's where we already were. But if we now leave our Milky Way galaxy, a million light years is very little. A million light years would be explained or expressed as the capital M of mega light years. That's a million light years. But very soon you will see that we need 1,000 times more, which is the giga light year, which is a million light years. Imagine that you travel for a million years with that crazy speed. We are around as our species, we are around for 200,000, 300,000 years. And this is a billion years. That's long before the solar system formed. So it becomes completely crazy to try to imagine the scale of this. I think we can basically just look at the numbers and go with it. That's really my advice. That's the only thing I can think of to get your head around this. In case you need to refresh your knowledge about the powers of 10, I have some basic physics lectures of old on my teaching days that are on my website about the powers of 10 notation. So a million is 10 to the 6. The one with 6 zeros. 10 to the 9th is a billion. And the prefixes are giga, mega, etc. Because of the computer language, you're kind of used to those. But I have different short summaries about these prefixes and also about the power of 10 notation, so-called scientific notation. We're going to use that a lot because I'm not going to type all these zeros when we talk about billions of light years. Anyway, so that's the idea of scale in this context. It really it doesn't make much sense anymore. At least it doesn't make sense to try to imagine, to build a scale model or something. So we are going deep. And I mentioned it has a double meaning. And in my view, that's why I came up with this title. We go deep into the universe over these huge distances to the edge of the observable universe. Of course, I will explain what that means later. But there is a certain edge to where we can observe. So that's going deep, but we go deep into the real questions about the universe, especially the cosmology part. So that's going deep into the study of the universe. It's amazing that this is just historically defined, that we use terms of solar neighborhood and local group. We are now leaving the Milky Way galaxy. The Andromeda, which is our next neighbor, is 2.5 million light years away. And that galaxy, plus a lot of other stuff, is what is called the local group. But this is typically in the order of 10 million light years range volume. And that's our local group. It really makes it clear that when we then start to talk about billions of light years, that the terminology is actually quite funny. But probably appropriate. The solar neighborhood, I think, is a term that came from, who was that? I'll come back to that, one of the historic astronomers. Anyway, so the Andromeda is 2.5 million. To come back to the range that we are going to discuss in this course, the edge of the observable universe, and I'll explain later what that exactly means, is 13.8 giga light years, it's billions of light years as we see it. And I need to, and this is a big part of what we're going to discuss, that we live in an expanding universe, and that means that edge where it was when the photons that we observe now, after 13.8 billion years, that edge is now much further away. So the edge of the observable universe is now, according to the theory, almost, just a little bit less of 50 billion light years. So that's the radius of what we call the observable universe. So that's just setting the scene of the scope, the scale of what we're going to talk about. There's an image by one of the famous deep field images by the Hubble Space Telescope. I'll come back to that. In the 18th century, and before, but it became really an interesting study object in the 18th century, that to look at, with whatever telescopes they had at the time, to look at fuzzy objects in the sky. And the only way to give a name to those fuzzy objects was to call them nebulae. But what was really exciting for astronomers of the time was to see if such a nebulous patch, observing it from night to night, if that would move, because then it would be a comet, which may become really bright in the sky with a tail and everything. And it was just a gimmick. I don't know how to say this. An idea of the time that as an astronomer you could really make name for yourself if you discovered comets. They could even be named after you, or you could become famous if you were the first one to say, hey, that little blob there, that's a comet, because it moves. And this is why it became popular to study those fuzzy blobs in the sky. Charles Messier was a French astronomer who was famous for that. And he made a catalog of about 100 of those fuzzy objects, which is the famous Messier catalog. We have M numbers for many deep space objects, not only galaxies, but all kinds of objects. And the M number means that they are in the Messier catalog. And then William Herschel, and he had a famous son as well. They were very active observers, had built his own telescope. They added many more of these nebulous objects, and that became the general catalog of nebulae, some 5,000 objects. And then there was another guy, Johann Dreyer, who published the catalog of nebula and clusters, NGC, and later that became the index of catalogs. I mention this because you still can see NGC numbers and IC numbers when we talk about objects. And that's the history of it, that there were these different catalogs that were set up by astronomers like those who were studying especially the fuzzy patches in the sky, hoping that they would discover comets. That was really the incentive. There was no idea to think about the concept of galaxy, anything like that at that time. In this context, Johann Dreyer, that was modern in those days, and then we started, and I'll come back to that, to figure out that there were things, some of these fuzzy objects were actually galaxies in their own right. And this comes back to something that I discussed last course, I think, as well, but it is historically very significant that just over 100 years ago, there was a debate between two leading astronomers of the time, whether the Milky Way, as we called it at that time, this fuzzy band in the sky, and we realized that we were in there, if that would be the whole universe, or if some of these fuzzy objects were actually outside what we call the Milky Way. That was a matter of debate. And these are top-notch astronomers. This was the famous great debate, an after-dinner debate at the conference in April 1920. 2020, we celebrated the 100th anniversary of that debate, because it is historically so significant that it shows how far we have come in just 100 years, in just in 1 century. Curtis, one of the opponents in the discussion, he said those spiral nebulae are outside our own galaxy. The reason that he thought that was that his idea about the size of the Milky Way was that it was much smaller than it actually is. And Shapley, the other guy, said, no, they are nearby, and the universe is one big galaxy, and that's what we call the Milky Way. We can laugh about this, but that's not really appropriate, I think, because this illustrates that the top-notch astronomers of the time simply had no way of resolving this question. Is the Milky Way all there is, or are these some of these fuzzy patches, are they further away than the Milky Way? Are we only in our own galaxy, and are there other galaxies out there? It started with, and this cannot be overestimated in its importance, with the technique that was basically discovered by Henrietta Leavitt. And I've discussed this before, because we talked about the Cepheid method of measuring distance in the previous course. These are variable stars. They have a light curve, which is very regular. So you can measure the period of the pulses. And they come in all kinds of periods. You have fast ones and slow ones and everything in between. And she studied them in the Magellanic Clouds, and realizing that that's a dwarf galaxy of our own galaxy, and realizing that these stars were all roughly at the same distance to us because they were in the same dwarf galaxy. She found a relationship between the brightness of these variable stars, the overall brightness, as you would see them in your telescope, compared to the period of their oscillation, of their fluctuation of brightness. That led to the famous period luminosity relationship. Because these stars are roughly at the same distance, she realized that the brightness could be interpreted as luminosity. I have talked about in the previous courses luminosity. We started about that with in the Leaving the Solar System course. I always refer to the wattage on a light bulb. It's the power of the star. We are just using a different unit. We use the luminosity of our sun as 1 unit, but it's the power output of the star. It's an intrinsic property of a star, and if you observe the brightness, if we see it, then the relationship between this brightness, if we see it, we call that magnitude, and the luminosity of the star is not a direct relationship, because it depends on the distance. A very bright torch at a very large distance, I gave you that thought experiment, would be very faint, but it would have a high luminosity, a high wattage. So what she realized is that because these stars were basically all at the same distance, that the brightness that she saw was a measure for the luminosity. So the brighter stars had a higher luminosity than the fainter stars. So she concluded correctly that if you can measure the period, you get a measure for the actual luminosity of a star. I've discussed this in detail in the previous course. I'm just reminding you here. You can go to the lectures on that in the previous course yourself in your own time. It's really historically very important discovery. The problem was that she didn't know, and nobody knew accurately what the distance was to the Magellanic Clouds. So she couldn't scale the method, but it was in principle, she realized that this was a very powerful way to measure distances. Once you would know the 0 point, once you would know you would have examples of Cepheid variables of which you knew the distance, for instance, because of parallax measurements or something like that. That's where it started, and it was in 1912. And then Shapley, he was one of the guys in that debate I was just talking about. He created what is referred to now as the Shapley period luminosity relation, because he observed, since he learned about this discovery by Henrietta, he observed many Cepheid variables in different locations, so at different distances. And he cataloged those, although he still had the same problem that he couldn't scale it because distance measuring is the real difficult problem that blocked the idea or blocked the understanding of sizes and distances in the universe. And this is why that debate was so typical for the time. They couldn't measure distances with any imaginable accuracy, not even roughly. But this technique of the Cepheid variables, that set the scene to solve that problem. This all happened in a few years' time, because Edwin Hubble, the famous Edwin Hubble, he studied from 1911 already with the Carnegie Observatory here, in the Carnegie Observatory here. He studied the Andromeda and the Trigillum nebulae, which are two galaxies nearby. I'll talk about those in details in the next lecture. He studied those, and with photographic images, obviously, because there was no other technique. We didn't have CCD cameras in those days. And then this is a very famous image. And the notes here are made by Hubble himself. And here, between those two dashes, there is a very faint object. And he had put an N there originally for novae. This was something that I hadn't seen before, and then you called it a novae. Very often, that turned out to be what we now call a supernova explosion. Suddenly brightening of a star, which you couldn't see beforehand. But his discovery, and I'm not sure if it was at this date or because this is in black and the correction he made here is in red. But at some point he realized that this one was a Cepheid variable star. So he said, he wrote down VAR exclamation mark. This is really a very historic image, because this gave him the opportunity to make an estimate for the distance to the Andromeda galaxy. The scale problem was still huge, but at least he could try to, based on what we expected to be the distance to the Magellanic Clouds, on that scale, to calculate what the actual distance to the Andromeda galaxy was. And he estimated that it was 929,000 light years. This was far too short because of the scale problem, but it didn't matter. It was big enough to settle that debate about whether there is stuff outside the Milky Way or not. The discovery was in 23. He published his results, first results in 24. So that was only 4 years after that debate, based on the method that Henrietta Swan-Leavitt had discovered, had devised based on Cepheid variable. That settled that debate. We now know that the Andromeda galaxy is 2.5 million light years, so he was more than 2.5 times wrong in a scale, but you can't blame him for that. We didn't know the scale for anything outside the Milky Way at that time. I've once suggested to some people here in New Zealand who have connections to the American Astronomical Society to celebrate this year at Christmas Day, because he gave a presentation on Christmas Day in 1924, which is actually exactly 100 years ago this year, to celebrate this as an event. I don't think it will come through. I don't care, but in my view, and I will definitely think about this on Christmas Day, that this is the 100-year celebration of this presentation that Edwin Hubble gave, that really settled the debate. So that discovery dramatically expanded the whole idea about what we know about the scale of the universe. And it settles that famous debate only 4 years earlier. So you see how in the early 20th century, things have evolved really, really fast. From not knowing what we mean when we talk about universe, until up to the point to realize that the Milky Way is just one island universe. That's a beautiful name that was given by Immanuel Kant, I think, the philosopher, as a name for a galaxy, island universes. That there are other island universes out there. Okay, so that was a bit of, I think, very important and also very interesting history to realize when we go deep and we talk about the Big Bang and what happened 30 minutes after the Big Bang and things like that. We're going to do that. But that it was only 100 years ago that we had to figure out these very, very basic questions. Okay, a little bit about distance units. Parsec, I talked about that when we talked about the parallax method of measuring distances in our term 2 course. It's still used by many astronomers. I hate it because it's completely irrelevant. Physically speaking, it's a completely irrelevant unit, but astronomers, they insist. But the conversion is that 1 parsec is 3.26 light years, or 1 megaparsec is 3.26 mega light years. If you want to, there are conversion calculators here, but you can convert between parsec and light years in both directions, if you want to ever do that. But I kind of remember the 3.26 light years for 1 parsec. The metric converter between kilometers and miles and things like that you can find here at that. I'll discuss this in more detail connected to the parsec, the parallax method of distance measurement in the course leaving the solar system. And then another aspect, which is, if we look back in space, because of the fast but limited, finite speed of light, we are looking back in history. We cannot see at a distance what is happening right now. We can only see what happened at the time that the photons left that object, the photons that we now receive in our telescope or in our eyes. This happens at any distance. This is my point here. If you take a photograph of a group of people in front of you, every 30 centimeters distance takes 1 nanosecond, the speed of light. And you can say, well, 1 nanosecond is not much. Yeah, but it's measurable. If I take a photo of a group of people, the person who's sitting furthest away is older, let me not make a mistake now, is younger on that photograph than the 2 people who are sitting more in the front. The age difference is only in nanoseconds, but it's measurable. We don't realize it in our everyday life because nanoseconds are not really critical in our everyday life, right? But my point is that if we say that our telescopes are time machines, we always look back in history, that this happens at any distance. Everything we observe visually is based on the speed of light. And because the speed of light is finite, it's not infinite, we always have that problem that we never can see what happens now if I take a picture, that the images on that picture are related to objects several nanoseconds earlier, before I took the picture. So I can never see what any of you, if I would take a picture of you as a group, and I had discussion in the observatory when we had face-to-face courses, and I could actually do this, and I could explain to them that somebody who was sitting further away in the room, they would be older on that photograph than the ones who were sitting closer. But none of them on the image would be as they were at the moment of the exposure. The moment of the exposure was when the photons that reflected from these different people actually all met up in the camera. Something to think about. But of course, in astronomy, it's a very well-known aspect that our telescopes, as we call them, are time machines. If you look at the Andromeda Galaxy, you see the Andromeda Galaxy as it was 2.5 million years ago. You can't possibly see how it is now. It's impossible. This also has an advantage, because this is how we study evolution in the universe, how things evolve. We can study objects at different distances and then compare them as being an observation of a certain type of galaxy or other object in a certain stage of its evolution. And we can compare that with another similar object at a different distance and see how that's, if it was further in its evolution or earlier in its evolution, etc. I have a way to try to visualize this, but I have a feeling that this is fairly confusing. The idea here is that if you look at a certain object at a distance a, one particular distance, and that object is evolving over time, over millions or billions of years, what you see is only at the moment that the photons left that object. So that evolution movie of that object is only one frame that you can see. So you see one frame of a movie. And then another object at a different distance or in another state of its evolution, you can see one frame of its own evolution movie. That's what I'm trying to say here. But astronomers can compare similar objects and observe different stages of evolution. And then they can kind of reconstruct a complete, more or less complete movie of that type of object. This is how we do astronomy. You may have thought about it and say, well, this is obvious, but I just want to make that point that related to the fact that the speed of light is finite. So we are looking back in history, looking back in time. And this comes to the more philosophical point. Haldane, the biologist, in 27, he already stated, and this is old-fashioned language, but now in my own suspicion is that the universe is not only queerer than we suppose, but queerer than we can suppose. We wouldn't use the word queer anymore, at least not in this context. But you can understand the idea. What he meant is that, especially the word "can" here, and this appeals to me personally very much. I'm thinking about it all the time. We are a species that have evolved here in the biosphere on this planet, and our neurological system is designed for survival, basically, like other animals. But somehow we evolved, and we use that mechanism that we have got, our neurological system. We become conscious, whatever you call that. Now we can ask questions, and we can try to look for answers. But how far can we get with that stuff that we have in here? We are just one particular life form, and the fact that we can ask these questions doesn't necessarily mean that we are capable of ever perceiving some sort of an answer to that. So that's what he really, that's how I interpret what he meant. is but queerer than we can suppose. There's a limit to what we can do. I came to this because Richard Dawkins, he's an evolutionary biologist. He gave many, many years ago, he gave a lecture. You can still find it on YouTube, I think. It's probably linked in the handout. And he made that reference to Haldane. And another comment he made, which I think is really important when we think about what we can understand as the life form that we are, as Homo sapiens, is that we live in what he refers to as a middle world between the micro world, the atomic scale world, and the macro world, which is the world of the universe as a whole. We live in that scale, which is in between those two. And he refers to that as the narrow range of reality. This is our everyday experience. We can only understand concepts if they are related to something in our everyday experience. If you would be an atom life form at an atomic scale, you would probably, your middle world, your range of reality, as he calls it, would be quantum mechanics. And any scale above that would be incomprehensible. And if you would be a life form with the size of a galaxy, you would probably think in terms of general relativity, and anything lower scale would be incomprehensible for you. This is and I think it's a very important philosophical thinking to realize that we are limited, and in this case, we are limited not by the neurological system that we have, but by the everyday experience that we have at the scale at which we are living. And we refer to that as the middle world. But jokingly, he said not Middle Earth, because that's Tolkien, but middle world. Anyway, so that's my kind of philosophical start of this whole course, is to make you think about those concepts. What can we understand? Here's some expressions of a Brian Greene, a very famous astronomer, but also a very famous educator. Life and consciousness is a fleeting phenomenon on the entire cosmological timeline, which in some sense makes us feel very small and very insignificant. This is really an experience which you will have when we talk about the things that we are going to talk about. And we already had that in the previous courses as well. But at the same time, it also emphasizes what we insignificant beings are able to do. The capacity to tell wondrous stories that help us deal with our own mortality and our own impermanence. Somewhere else he said, we are capable of writing the Fifth Symphony, Beethoven. We can paint the Mona Lisa. So these are examples of how far we can go. And you can extrapolate that, of course, in the scientific direction. Is what are we capable of? And you will be astonished with me, especially when we get into the cosmological part of this course, about how much we know about the first few seconds after the Big Bang, based on our understanding of fundamental physics. This is of particle physics. This is really astonishing what we can figure out. But my point here is that at the same time, we must realize that we are, by definition, limited, because we are who we are. We have just evolved only in the last 200, 300,000 years in this very thin layer, which we call the biosphere, on an insignificant planet somewhere. So, yeah, we are very small and insignificant. At the same time, we should be proud, and we should really enjoy that we can do as much as we actually are doing in terms of the science that we are developing. This is really my point here. And this is a famous cartoon, not a cartoon, it's a graphic by Maurits Escher, famous Dutch graphic artist who had a very, very wide imagination and creativity. This is the point that because we have evolved on this planet in a biosphere through billions of years of evolution. We can think about ourselves, oh, we understand everything, and we study and we build a bigger telescope, and then we can find out more. But if we study the universe, we are studying ourselves, because every atom in our body once was in a star system that exploded. There were elements which can only have been created with the merger of neutron stars, which is one of the most violent processes in the universe. Gold, for instance, and other higher range elements. I discussed this before. It's called the what is it? Archaeo. Anyway, doesn't matter. I'll come back to that sometime. That's the genesis of elements. Where our elements in the periodic table come from. So every atom in our body once was in these systems. And we are now a collection of atoms. And we can think very highly of ourselves. But we will pass away, and these atoms will go their own way. And in 4 or 5 billion years from now, the Earth will have been usurped by the star that we come out of, the sun, and the star itself will end its life in a planetary nebula. So these atoms will then disperse into space again. And there's a new star system can be built out of that. So this is kind of a way to look at not only at our own impermanence, but at the fact that we are part of this. We are not only in the universe, we are part of the universe. So in that context, in my view, it would be really good to conclude that we are basically studying ourselves when we study the universe. And this is where this graphics comes in, which I really like very much, because for me, it gives that message. It's the hand coming out of the paper, drawing itself. We are studying ourselves when we study the universe. Okay. This is a bit of a philosophical start of this course, which is on purpose, but also talked about the unimaginability of the scale and some other aspects, units that we use, etc. So that's the introduction that I wanted to give you, and I start with. What is cosmology? We will go into that. More than half of this course will be cosmology. It studies the universe as a whole, as a big volume. And because we will find out that we live in an expanding universe, space is expanding. That means that if you wind back that movie, as it were, in the opposite direction, then it must have started somewhere, and this is what we refer to as the Big Bang. So that's essentially what is cosmology. It studies the universe, the evolution of the universe as a whole, as a volume. We don't talk about galaxies and clusters of galaxies in that context anymore. And we need a lot of sophisticated physics, also mathematics. I'm not going into the formulas, of course. We need, as I mentioned already, we need relativity very much. That's the study of the evolution of the universe is based on the theory of relativity, the general theory of relativity. That's it. If we wouldn't have that theory, there would be no cosmology to speak of. We would still be consider it to be a philosophy, like in the ancient day, in the old days. So it's all based on general relativity, and I'll definitely go in there when we actually talk about the cosmology, or the Big Bang cosmology, as it's called. And I'll show you some formulas, but it will be manageable. I'm not expecting you to understand tensor algebra or Riemannian geometry or anything like that. I would be struggling with that myself. But that's cosmology. That's where we are going in the second part. It's roughly 2/3, I think, of this course. So we started looking outside of our own galaxy only 100 years ago, realizing that there is something outside our own galaxy. We now have traveled to what we call the edge of the observable universe. And that's a fantastic story, which basically has unfolded over the last 100 years only. This is an interesting book in this context. It's in the American edition is called The Edge of Knowledge. The British version is called The Known Unknowns, I believe. I have this version. It's only the title which has changed. It's the same book. Very recent by Lawrence Krauss. I can really recommend this. He really goes into concept of space, concept of time, etc. And he identifies where the limitations are, of where we are hitting the brick wall, so to speak, in our understanding of physics, which is related to the to cosmology and the study of the universe. Okay.